All right, this is your lesson on solving quadratics. We're going to look at 6-2 first, which is in the textbook. And it's actually going to build off of your Algebra 1 content knowledge where we're solving quadratics by graphing. Okay? One of the first things that we should do when graphing a quadratic is find its axis of symmetry. So if you recall, to find the axis of symmetry, it's just negative b over 2a. Axis of symmetry is just going to be essentially our midpoint, actually, of our parabola, okay? So notice I plugged in my value for b, which was 6, and my value for a, which is 1. So we really have negative 6 divided by 2, which is going to be negative 3, okay? What I'd like for us to do on our xy table is place this axis of symmetry smack dab in the middle. It's going to be most efficient when it comes to finding values to plug in, because actually anything that's equidistant from the axis of symmetry will have the same y-coordinate. So negative 2 and negative 4 will actually both have the same y value. So let's plug in negative 2. It'll make our job a lot easier. So we have negative 2 squared plus 6 times negative 2 plus 8. Negative 2 squared is 4. 6 times negative 2 is negative 12. And then we have plus 8, which equals 0. And that was actually the whole purpose in us solving by graphing, was to find our zeros. Zeros are solutions, and solutions are x-intercepts. So if I go to graph it, this is actually where it's going to cross the x-axis. Something that I forgot to do was to plug in my axis of symmetry. So silly me, I'm going to go back and retrace my steps. So when we plug in negative 3 into our function here, negative 3 squared is 9. We get a negative 18, and then we get a plus 8. That's going to simplify to being negative 1. Okay? So now, if I start to zoom in here to plot my points, so at negative 3, we're at negative 1. Oops, gotta get my pen on. And then at negative 2 and negative 4, I'm actually crossing over here. And then actually, I'm just going to connect my dots, because the whole purpose of this was actually just to solve by graphing. And when I'm solving by graphing, I'm just looking for where I cross the x-axis. All right, we're going to solve this next one by graphing as well. So we first actually need to get our 16 onto the other side by subtracting him onto the other side, okay? So we're going to get negative x squared plus 8x minus 16 is equal to 0. Once again, I'm solving by graphing, so I'm going to look for where I cross the x-axis, okay? All right, so first off, let's find our axis of symmetry. So we plug in our value for b, and our value for a is negative 1. So we have negative 8 divided by negative 2, which is positive 4. All right, so if we plug in 4 into our equation, we actually get 0. So in this scenario, this is actually where we only have one solution, because our axis of symmetry is our 0, or our x-intercept. Something else that we can recognize is the fact that it's negative x squared, so that means I'm going to open down, okay? And because the whole purpose of this problem was just to solve, I'm actually done, because I have already identified where I cross the x-axis, and I just cross them once at 4. All right, so let's continue on and look at example 3, where we're actually given a problem that's very common to see on an ACT or an SAT. So we have these two numbers. Let's let one of them be x and one of them be y, okay? The sum of these numbers is 6, okay? So let's let one number be x, okay? And y, this is where your textbook started to get a little bit ahead. So x plus y equals 6. So if we get our other number isolated, our other number is equal to the quantity of 6 minus x. So notice that we put both of our numbers now in terms of x, okay? And their product is 10. So if I take these two numbers, we have x and 6 minus x, it's equal to 10, okay? So then I just have to FOIL. We have 6x minus x squared, and we're going to subtract 10 and get it equal to 0. So if I rewrite this in proper standard form, here is my equation. And now I'm going to solve him by graphing. So first off, I'm going to find my vertex. Negative b over 2a, my axis of symmetry. So negative 6 over 2 times negative 1. That tells me that I'm going to have an axis of symmetry at positive 3. Okay? And if I plug 3 into my function, I find that I actually have a y-coordinate of negative 1. So if I zoom in, oops, there we go, 3, negative 1. Something that I'd actually like for us to notice in logical sense that we were not wasting our time plugging in other things is the fact that because our leading coefficient, the leading term x squared, has a negative coefficient, I'm going to open down. So once again, because I'm opening down, I'm just going to draw that general shape. Notice that I never cross the x-axis. So this is a scenario where I do not have any real solutions, but now that we know about complex numbers, we can actually find his solutions using the quadratic formula or completing the square. But because we're on a graph, we cannot identify the imaginary solutions. All right, so now looking at example 4, not always will our roots be nice numbers. So we're going to start to approximate here, okay? So once again, I'm going to make my xy table, but I'm first going to identify what my axis of symmetry is, so negative b over 2 times a. If I plug in my b value of 4, I have negative 4 over 2 times negative 1. Negative 4 divided by negative 2 is positive 2. If I were to plug in 2 into my equation, I would get back a y value of 3. Now I'm going to go equidistant away from my axis of symmetry, so I'm going to plug in x is 3 and x is 1. Notice they are both the same distance away from our axis of symmetry. Once again, I'm now going to just simply plug it in. I'll actually show my work for this one. So 1 squared is 1, and then we get negative 1 plus 4 minus 1. That's going to get us a y value of 2. Notice we have not yet received a y value that has dipped into the negative numbers, so we're still in the positive range. So now I'm going to keep going, and I'm going to do 0 and 4 because these are both now 2 units away from our x-axis, okay? Or I'm sorry, our axis of symmetry. And it makes the most sense to plug in 0, but we don't need to plug in 0 because it's going to make any term with x disappear, giving us a y value of negative 1, okay? So for both of them. Zoom in here. Oops, there we go. And now we plot our coordinates, okay? So at 0, I'm at negative 1. At 1, I'm up at 2. Notice that I crossed over the x-axis between 0 and 1. At 2, I'm at 3. And then once again, I'm dropping down 3, 2, and 4, down to negative 1. Okay. There's my terribly drawn parabola. It's an attempt, right? All right, so I'm noticing I'm crossing the x-axis between here and between here. So this x-intercept, this solution is between 0 and 1. And this guy here, he is between 3 and 4, okay? And these are the consecutive integers to which these solutions or these roots are located. So I just want to do a little side note for the next example on the next page. Your example 5 actually is going to walk you through how to start using your technology. And it's going to use a more advanced equation, but don't worry, it's still going to be treated the exact same. So I want you to try example 5 on your own, and I'd like you to investigate how to use the TI-83 or 84 graphing calculator to actually calculate the exact location of a 0. All right, so we're picking up with 6.3, the section in Glencoe about solving quadratic equations by factoring. The lesson for 6.2, where it's graphing, will be in a different file. All right, looking at example 1, where we have to solve each equation by factoring. I first have x squared equals 6x. Something I must do is get the equation set equal to 0, so I'm going to subtract 6x from both sides of my equation. Okay? So now we have x squared minus 6x equals 0. So to factor this, I'm noticing that they have a common factor of x. So I can factor that out of both of my terms, and I now have these two factors. So I'm going to set both of my factors equal to 0. Well, the first one's not so bad. First factor is x, so x must equal 0. Now x minus 6, when I set him equal to 0, I find by adding 6 to both sides that x is equal to 6. And these are my two solutions for this first problem. Let me put them in red, that way they stand out. The next one, once again, I need to get it set equal to 0, so I'm going to subtract 15, getting me 2x squared plus 7x minus 15 is equal to 0. Okay? Well, to factor this, I'm going to create my two sets of parentheses. So I know that one of them has to be 2x and one of them must be x because 2x times x is how I get 2x squared. But now I need to think about what multiplies me negative 15, and when I start foiling it out using this 2x, something's going to have to produce a positive 7x. Well, that's going to get me a negative 3 and a positive 5, because when I FOIL this out, I'm going to end up with a 10x and a negative 3x producing a 7x, okay? So now, once again, I'm going to set my factors, both of them equal to 0, and solve. First, for this one, I add 3 to both sides. So then we have 2x equals 3, and then I divide by 2, so we get x is equal to 3 halves. Now, in the other one, x plus 5, when we set him equal to 0, we subtract 5 and get a solution of x equals negative 5. So here are our solutions. An observation. Notice whatever the sign is inside a quantity of parentheses, we're getting the opposite sign for our solution. So we can't assume that positive 5 would be a solution because it's really going to be negative 5 that would make that quantity equal to 0. All right, what about example 2? Example 2 is already set equal to 0. Now, if you remember your Algebra 1, you'll notice that this is the example of a perfect square trinomial. So this is going to factor into x minus 8, that quantity squared. And whenever I have a factor squared, this tells me that it's actually going to be one root, but it's going to be considered a root twice. Now, in another connection, it means that I'm only going to cross the x-axis once at this location. So when I set this factor equal to 0, x minus 8 equals 0, I'm going to get x is equal to 8 as my one and only solution. He is a root twice, but an x-intercept once. All right, let's continue on with 6-3, solving by factoring. In this next question, I'm told to find the positive solution. So let's continue. First things first, GCF. The GCF is a GCF of 3. When I factor a 3 out of all my terms, I'm left with x squared minus x minus 20. Okay? Now, I really don't need the 3 here. I could have actually just divided everything by 3 because it's an equation, and 0 divided by 3 is 0. So now I really don't care about him. He's not going to give me a solution. So now I'm going to factor this, and I ask myself what multiplies to be negative 20 but adds to be negative 1. Well, that's going to be a negative 5 and a positive 4. Now, we already discussed the fact that it's always going to be the sign opposite inside your parentheses. So when you set it equal to 0, x minus 5 equals 0, it's going to give us a solution by adding 5 to both sides of x is equal to positive 5. I don't even need to worry about this x plus 4 because I know it's going to be the opposite sign. Now, what about the case where I'm given the roots and I need to write an equation? I'm going to need a little bit more space here. This is essentially going to go in reverse. If we have a root of negative 5, this means that it was a factor at one point, and we had set its factor equal to 0 at one point. So all I need to do to get it back to being set equal to 0 is adding 5 to both sides, giving me the expression x plus 5 equals 0. Well, here's one of the factors. Now, what about the other one? The other one we have is 1/2. So we know that 1/2 was a solution. Well, this was set equal to 0, and I'm going to stray a little bit from the textbook because I don't like fractions. I'm going to multiply both sides by 2, giving me 2x is equal to 1. Now I'm going to subtract 1 from both sides, giving me a factor of 2x minus 1 equals 0. Well, now I have my factors. I have x plus 5 and 2x minus 1, so all I need to do is FOIL it on out. And I'm going to let you FOIL it on out and check your answer with the textbook. All right, so we're going to continue on to 6-4, the chapter about completing the square. We're going to use the square root property a lot in this chapter, so it's going to be important for us to learn about what perfect square trinomials are. In this scenario here, it looks like I want to get it set equal to 0 and factor it, but I don't need to do that here. Notice on the left-hand side, it's going to produce a perfect square trinomial of x plus 5, because 5 times 5 is 25 and 5 plus 5 is 10. So now it'll be really easy to take the square root of both sides. Now notice, whenever you take the square root of a quantity, you're going to end up with a positive or a negative. And the reason that is because that quantity in parentheses could have been positive or negative, because a negative number squared would have given you still a positive 49. Okay? So now we have the plus or minus the square root of 49. So that tells me I could be positive or negative 7. Okay? So to help myself stay organized, I'm going to create my two separate equations. X plus 5 equals positive 7 and x plus 5 equals negative 7. And for both of them, I'm just going to subtract 5. So we get the solution 2, and we also get the solution of negative 12. All right, let's continue using the square root property. Notice in this scenario, once again, I can create a perfect square trinomial of x minus 3 squared. And it's going to be equal to 32. Now I could take the square root of both sides, getting me x minus 3 is equal to the positive or negative square root of 32. Now we need to simplify our radical. In 32, that gets me 16 and 2 underneath my radical. So really, I just have to pull out the 4 because the square root of 16 is 4. So we have x minus 3 is equal to the positive or negative 4 radical 2. Lastly, all we need to do is add 3, and x is equal to 3 plus or minus 4 radical 2. Now your textbook will go farther and use decimal answers, but I would much rather you stay here. Leave your answer in simplified radical notation. And notice that I have two solutions because of my plus or my minus. Now what about scenarios where we don't have perfect square trinomials? That's when we learn the process of completing the square. The process for completing the square is always going to be the same. We're always going to take a look at our b value. In this scenario, it's 12. And we're going to take that 12 and we're going to cut it in half. And then whatever that produces, I'm going to square it. Okay? So 12 cut in half is going to be 6. 6 squared is going to be 36. So my value for c is 36. And now we're going to create a perfect square trinomial of x plus 6 squared. An observation. The quantity that goes inside of here is always half of my b. Did you notice that before? Now let's actually use completing the square to solve an equation. So in this scenario here, notice that I cannot create a perfect square trinomial. So I'm actually going to add 20 onto both sides. So we have x squared plus 8x is equal to 20. Now I gave myself some space because I would like to be more visual, and I'm going to give myself a square on both sides of my equation, because what I do to one side, I must also do to the other side. To complete the square, I'm going to take 8, and I'm going to cut him in half. That's 4. 4 squared gets me 16. So now, on the left-hand side, that'll create the perfect square trinomial of x plus 4 squared, and on the right-hand side, 20 plus 16 is 36. So now we're going to take the square root of both sides, simplifying x plus 4 is equal to positive or negative, well, the square root of 36 is 6. So we have this case where we're going to have x plus 4 is equal to 6, and we're going to have the case of x plus 4 is equal to negative 6. In both of them, I'm going to subtract 4. So we have x is equal to, well, 6 minus 4 is 2. Over here, we're going to have x is equal to, well, negative 6 minus 4 is negative 10. So here are my two solutions. Now what about when your a is not 1? When your a is not 1, it gets a little bit more messy. All right, so when your a is not 1, we're going to have to divide away the a. So I'm going to divide everything by 2. So then we're going to have x squared minus 5 halves x plus 3 halves is equal to, well, 0 divided by 2 is still 0. So now I'm going to move my constant term onto the other side of my equation. So we have x squared minus 5 halves x is equal to negative 3 halves. Once again, notice I'm leaving room for myself to complete the squares, and I'm giving 1 to both sides because I need to balance my equation. So now, negative 5 halves. I'm going to cut him in half, and then I'm going to square it. So half of negative 5 halves is going to be negative 5 fourths. Negative 5 fourths squared is going to get me 25 sixteenths, because all I'm really doing is squaring the top and the bottom by my quotient property. Now this is going to produce our perfect square trinomial of x, and remember the pattern, it's always going to be half, so minus 5 fourths squared. On the right hand side, it'd be really helpful to have a common denominator, so I'm going to change negative 3 halves to having a common denominator with 16. So 2 times 8 got me 16, so negative 3 times 8, that's going to be negative 24. So negative 24 sixteenths plus 25 sixteenths gets me 1 16th. Now I'm going to take the square root of both sides. We have x minus 5 fourths is equal to the plus or the minus. Well, the square root of 1 16th is 1 fourth. So now we can create our two separate equations just to kind of space things out. So we have x minus 5 fourths is equal to positive 1 fourth. And we have x minus 5 fourths is equal to negative 1 fourth. For both of them, I'm going to add 5 fourths. So over here, we get x is equal to 6 fourths, which simplifies to 3 halves. Over here, when we add 5 fourths, we get negative 1 fourth plus 5 fourths is 4 fourths, or simply 1. All right, we're going to finish up 6-4. Once again, notice on the left-hand side, we cannot create a perfect square trinomial. So we're going to subtract 11 from both sides, getting us x squared plus 4x is equal to negative 11. Once again, I'm going to set myself up to complete the square, add a square onto both sides. I'm going to take my 4, cut him in half, which is 2, and 2 squared is 4. So now the perfect square trinomial produced is going to be x plus 2 squared is equal to, well, negative 11 plus 4, that's equal to negative 7. So now I'm going to take the square root of both sides, and I get x plus 2 is equal to the positive or negative. Well, think about it. The square root of negative 7. The square root of a negative means I can pull out an I, and I can't simplify the 7. So last thing I need to do is subtract 2, and we get x is equal to negative 2 plus or minus I radical 7. Well, look at that. We just got an imaginary answer. Factoring couldn't do that, could it? It only produces rational answers. All right, in 6-5, you talk about the quadratic formula. Quadratic formula is essentially just plugging things in, but you need to first identify your A, your B, and your C. In a problem like example 1, we need to subtract 28 to the left-hand side so that we can more clearly see all of our values. Not to mention, we're solving, and solving means it's equal to 0. So here we have an A value of 1. We're going to have a B value of negative 12. And we're going to have a C value of negative 28. Okay? So the quadratic formula, it reads as follows. We have negative b plus or minus the square root of b squared minus 4ac all over 2a. Well, let's fill in the pieces that we know. We know that our a value is 1, so we don't really need him in the denominator, and we don't really need him in our quadratic formula at all. Something else we know. We know our b value is negative 12. So in the front, we're going to have a negative 12, which is just going to produce a positive 12. On the inside, we're going to have to input a negative 12 squared. So I'm going to make sure I put in my parentheses if I don't know what negative 12 squared is equal to. All right, the last one we need to fill in is C. So over here, we're going to fill in negative 4 times negative 28. So now, it just is going to take me simplifying my radical. So we have negative 12 squared is 144. And a negative 4 times a negative 28 is going to be a positive 112. And it's all over 2. So now, under the radical, 144 plus 112 is 256. So then take the square root of 256, and we get 16. We can break it up into our two cases where we have 12 plus 16 over 2, and we have 12 minus 16 over 2. And in our first one, 12 plus 16 over 2, that gets us 14. And in our second case, 12 minus 16 over 2 gets us negative 2. This really takes a lot of practice, and you have to make sure you're following the rules of algebra. So I'd like for you to try examples 2, 3, and 4 on your own and check your answer in the textbook. I'll meet up with you again when we talk about the discriminant. Alright, the very last concept in this section is the discriminant. And hopefully you notice that the discriminant is the quantity underneath the radical of the quadratic formula, which is why it dictates the type and number of roots you're going to have for your quadratic equation. So we just need to remember discriminant, that's going to be b squared minus 4ac. So we just need to properly identify them here. So in our first example A, b is negative 12. So we have negative 12 squared minus 4 times, our a value is going to be 9, and our c value is going to be positive 4. Well, negative 12 squared minus 4 times 9 times 4 gets me a value of 0. This means that I have one root, because the square root of 0 is only ever going to be 0. And it's going to be real. And something else you can recognize is going to be a rational root, because you're automatically only going to end up, if we think about it, negative b plus or minus 0 over 2a, we're only going to ever end up with this chunk right here. Alright, I'll do one more with you, then I want you to try them on your own. Let's together look at, how about D? So once again, our b value here is hidden. He's negative 7. Notice he looks like he's our leading coefficient, but he's actually not. Negative 7 squared minus 4 times my a value of 15 and my c value of negative 4. Well, this expression, negative 7 squared minus 4 times 15 times negative 4 is 289. Well, notice that 289 is actually a perfect square. That's 17 squared. So no matter what, I'm going to have a plus or minus 17. So that's going to give me 2 roots. They're going to be real, but they're going to be nice numbers. Think about it. Negative b plus or minus 17 over 2a, those are going to give me rational numbers. I'm only ever going to have irrational numbers if it's not a perfect square. Try b and c on your own and check your answers. Alright, so this next section is kind of a toss-up. It's kind of in the solving section, but it's also kind of part of graphing quadratic inequalities, which we will do when we get back from spring break if you're taking this in the spring. If not, I don't really know when we're going to be taking this because, well, it's the future. Anyway, so we are going to graph our inequality, and then we are going to do the same protocol as we do for linear inequalities. We're going to use a dashed or a solid line, and we're going to shade. So first things first, let's find our axis of symmetry, negative b over 2a. So we have negative 6, so positive 6 over 2 times negative 1, so we have an x value of negative 3. When we plug in negative 3 into our lovely equation here, quickly typing that out, or writing that out, so we have negative 9 plus 18 minus 7. Negative 9 plus 18 is 9, and 9 minus 7 equals 2. So if I zoom in here, we have a coordinate at negative 3, 2. Draw that little spot. Alright, so now we're going to make an xy table here, okay? So smack dab in the middle, I'm going to put negative 3, 2. And then I'm going to plug in either negative 4 or negative 2. Now, it would make more sense for me actually to plug in negative 2. They're both the same distance away, so it doesn't matter which one I plug in. So we're going to do negative 2 squared minus 6 times negative 2 minus 7. So we end up with negative 4 plus 12 minus 7. Negative 4 plus 12, that's going to get me positive 8, and 8 minus 7 equals 1. So then at negative 4 and negative 2, we have y values of 1. Plot them, plot them. All right, another point that we can use is the fact that negative 7 is going to be our y-intercept. So I can also plot that. It's going to be down here. And I'm just going to connect the dots you should probably have more precision than I do. If I plugged in -1 and if I plugged in -5, this would help, and I would like for you to do that. But let's just discuss how to shade. First off, I know I'm going to have dashed lines. Let me give myself my dashed lines here because we are not an or equal to inequality. Now, if we read it out loud, y is greater than. Greater than, we shade above. So we're going to shade above this parabola. The method used in your textbook is just using a tester point, and that is the exact same strategy. And you can use whatever logic you would like to on this one. All right, so I'm actually going to take a different approach to the one in the textbook, for example, 2, and I'm going to solve it by factoring, okay? So I'm going to factor my left-hand side here, and it's going to produce an x minus a 3 and an x plus a 1, okay? Which gives me a 3 as a possible solution and a -1. And if we graph these on the number line here, -1 and 3, both are going to get open circles because we are not or equal to's. What I'm going to do to determine where to shade is I'm going to pick a tester point, and I'm going to pick 0. Plug in 0 to see if that part is true, aka where I should shade, okay? So my original equation, 0 squared plus 2 times 0 minus 3, is that greater than 0? Is -3 bigger than 0? No. Therefore, we're not going to shade in the middle. We're going to shade on this side and this side, but you can also pick a tester point on either side. So this actually is going to be an or inequality, getting us the answers where x is less than -1 or x is greater than 3. All right, I'm going to keep on solving these using other methods, but I'm actually going to skip a step in this next one. So first off, like the textbook says, we're going to use a quadratic formula here. So I want you to plug this into the quadratic formula and find out what you get. You should get approximately for your solutions 2.47 and -0.14. So then I'm going to use the same strategy I did in the last one, plot them on the number line, and I'm going to test a value in between them. Okay, now these locations here, they will be solutions because we are or equal to, so they get shaded circles here. So if I pick a spot in the middle, 0 being the best one, plug it in, is 0 greater than or equal to 0 minus 0 minus 1? And it is. So therefore I'm shading between these two locations. So we are located between them. So x is going to be between -0.14 and 2.47. All right, so in our next one, once again, I'm going to jump around and use some strategies. So in this question, we have this formula, this function given, and we're trying to figure out where we are within 5 meters of the ground. So essentially what this means is, when is this equation going to be less than or equal to 5 meters of the ground? Okay, so ground meaning the zeros, okay? And if anything is less than 5, it's okay, okay? All right, so if we get our equation set equal to 0 plus 20x, and then we're going to subtract 5 from both sides, getting me subtract 4. Once again, I want you either to use the quadratic formula, or like the textbook says, you can use the way to calculate your zeros on your calculator, okay? So then, when you use the quadratic formula, you get your decimals, or if you use your calculator, you're going to have tester zeros located at 0.21 as well as 3.87, okay? And so, what we can do in this problem is, once again, we can plug in a value between them, like 1, okay? And determine whether or not it is true, okay? And so what we end up finding is the fact that we are actually needing to be less than 0.21 as well as greater than 3.87, because as the textbook is actually saying, is this is actually where your graph is lying below the 0 line, okay, which is where this part came into play.